I mean, I do give an entire course on just bandits, but 540, 541 or 543, I don't know what the course number is. You go to my website. I only teach 2 courses, machine learning and interactive machine learning, which is bandits.
Okay.
And
I'll have to take a look.
I'll start teaching reinforcement learning.
Oh, wait.
A theory of reinforcement learning. I don't actually implement anything. Well, I implement lots of things in bandits, like, so they're extremely practical. I would say reinforcement learning is completely impractical and not very useful. It does some cool video games, but other than that, not very useful.
I've seen reinforcement learning as very like theoretically interesting, not even in a mathematical sense, but just like abstractly, because it's like learning essentially in a more shallow, also like manner where like you don't have to define things in certain ways. You have to like just supervise learning, but it also just doesn't work as well. Right?
Yeah, it just the sample complexities are out of control. Meaning, like, it would just reinforcement learning has the power to learn anything, but there's not enough time in the universe to learn anything. Mostly because our algorithms are so bad. And our algorithms are so bad because the theory is so bad. And so that's why most of the people working in reinforcement learning are actually working on the theory. And there's very few people doing applied. I mean, okay, that's wrong. There are lots of people doing applied stuff, but like they're also like hitting a wall. Like there hasn't been a ton of advancement in reinforcement learning. Like you look at you would be right to throw progress like AlphaGo and Alpha StarCraft in my face as refuting that evidence, but like Dimitris Bertsakis has a great talk. He's basically going around. He wrote like the books on reinforcement learning back in the day, and he's basically saying that all these algorithms that DeepMind is coming up with, they're rehashing the exact same ideas. Like they are precisely the same algorithm that was used in the 80s and 90s. All they've done is they've like switched out like a small neural network for a very, very large neural network. That's like the only thing that's changed. And so we haven't really progressed as an academic field. We've just sort of like swapped out one small model for a big model. Our understanding has not increased. And that's why RL theories.
Can I ask a question
Yeah.
related to that? So this might be a very uninformed question, but I've always kind of seen that like supervised learning is a subset of RL because you could frame any supervised learning task as reinforcement, or just like, well, sort of.
I mean, maybe, yeah.
Do you think it'd be interesting to pursue, from a more theoretical perspective, like using that as a kind of bias towards finding algorithms which are effectively identical to supervised learning in some sense?
I mean, like, there's lots of, so like offline reinforcement learning is changing reinforcement learning into supervised learning. But we're getting a little bit ahead of ourselves.
Sure.
So maybe what I'll do is I'll write down sort of like a very basic RL problem, and then I will tell you how it relates to bandits, and then I'll prove a theorem about bandits.
Sure.
Okay, so let's say we have S states, A actions, and then we have S1, S2, and this is like if you took A1 with some probability. So you think of it as it's just like a 3-state system. It's kind of boring. But basically, taking action, A, T, so the way the game works is for little h equals 1, 2, ... h, the player, so we start in state 1, S1, and then for little h equals 1 to h, the player is going to choose some action, chooses AT, picture reveals, let's say, RT of STAT, and then ST plus 1 is drawn from P dot ST AT. So P is this transition kernel. So basically, if you're in state ST, let's say, at some time, let's say S2, then if you play action 1, with some probability you go to S1, with some probability you go to S3, with some probability that you self-loops, you go back. And like a really common example of this is like your car, and maybe you drive your car for a while and then it breaks down or overheats. So in a normal driving operating condition would be a state, and then in like overheating would be another state, and then but in that state it then cools down so that it could return back to its drivable state, or you could keep driving it in the bad state and just like kill yourself, or like kill the car, and then you're stuck in that state forever. But it's all probabilistic because it's not like, the things are not for sure things. And we're going to be playing a finite horizon game, Horizon H. And so you're going to get some reward. So for t equals 1, 2 to big H, the player's going to choose some action in the state, starting with S1. He's going to get some reward of R of ST AT. The rewards are unknown. And then he's going to transition to a new state, ST plus 1. This transition kernel probabilities are unknown. So P and R are unknown in advance. And then the objective, of course, is to obtain as much reward as possible. Maximize. Find a policy. Pi, which maps states to actions, that maximizes the reward. Okay. So you're going to play this game multiple times, you're going to explore around, you're going to be taking different actions, see where you end up. And so we're going to call this one of these things an episode. Is a single episode. And basically, the player is going to have access to multiple episodes. So he can play, as soon as he hits time H, the game's going to reset. And then he can play again. He starts in S1, he plays different actions, he explores what states and actions leads to what new states. And the objective is to basically navigate this MVP to get to areas of high reward so you can accumulate as much reward as possible. Okay? And so this problem, if we want to do this in an online setting, we want to basically accumulate as much reward over time. Okay, so there's like two kinds of games. There's the pure exploration game, where I just want to find some policy. It doesn't matter how I come to learning that policy, but at some point in the future I want to output something good. Or there's the online version, where I want to, while I'm learning, I also want to get closer and closer to a good thing. And so while I'm, if pi star, so if pi star is an optimal policy, maximizes RSH pi of SH, where again this policy is mapping from states to actions. So it's just sort of learning this rule of whenever I see this state, I'm going to play this action and repeat. So if pi star maximizes this quantity, then if I'm going to be playing for k episodes, so big K episodes, I'm going to play this game multiple big K times, then my regret is equal to just the expected value of my regret is the difference between what the optimal policy got on episode K. So there's some true best policy out there, and that's one I should play every single time. But what I played was on episode K was pi k. I chose on episode K to play my policy pi k, and then I received this amount of reward. Okay? And so I defined the regret over this whole time period as the difference between the amount of reward that the optimal policy got versus the amount of reward that I received over that same time period. And the big result is that there exists an algorithm, Hazard et al., 2017, that has regret, call it RT for short, or RK for short, less than or equal to H cubed SA K. Okay. So this is pretty good. And the reason why I'll walk through why this is kind of an interesting result. So first, so you're playing for H time steps, and let's say that the reward, let's say you also know that it's bounded between 0 and 1.
Just to clarify,
Yeah.
so S and A, there are just the sizes of these sets, right?
Yeah, S is the number of states and A is the number of actions. And I'm assuming that I have the same number of actions at each state, but they can do different things in different states. Think of Mario, the state of the world, which is the pixels, and the action could be whatever buttons you're pushing.
So,
Discrete action set.
so there exists an algorithm, meaning like something that finds the policy, the like optimal policy that has regret less than that.
Well, that's very interesting. It's not necessarily finding the optimal policy. It may never actually find the optimal policy, but it will get arbitrarily close.
Okay.
Because what it's saying is, so this algorithm at each time k, at each episode k, it's going to choose some policy pi k. And then over time, over big K episodes, this is the total amount of regret that this algorithm occurs. So like, let's put this in perspective. If you just played some random policy, like some fixed, you're just playing random actions in every state, then what's gonna happen is that relative to the best policy, there's always gonna be some constant gap between what if the best policy would have gotten a reward of 0.1 or 0.8, and you played some random action and expectation you get a reward of like 0.5, that means on each episode, at that time, you're gonna get a gap of 0.3. And if you suffer that at every single episode, then this regret bound would scale as k times 0.3, right? Times other things. But like, the point is that a trivial algorithm, or an algorithm that does not converge to the best algorithm, the best policy, will always get linear regret. Okay, so that's what a trivial algorithm would do. And what we want is an algorithm. The reason why this is remarkable is that what this says is that effectively you are converging to the optimal policy, because as big K gets very large, this is sublinear in K. Said another way, the average regret, so this is accumulated all my regret. If I just look at the average regret over time, so like on average, how much regret am I getting at some kth time, or at the kth time, you would divide this number by divide this number by K. And so really you're learning at this 1 over root K rate. Another picture to have in your mind is that like the regret, so the total reward is equal to, total, optimal reward you could have gotten minus the regret, right? K times. So if this is less than or equal to root K, then the total amount of reward you're getting is approaching sort of K times the optimal, because K is growing much faster than root K. And then also, because we have number of states and actions, if the state space is very large, then you have to really explore the MPP. You don't know where to look, and so you're really gonna have to search around, and so it's natural that the regret would have to scale with the number of states. Same argument, if the action space is very large, you're gonna have to try a lot of actions. So it's natural that this bound would scale with S times A. And it also scales with the horizon. And this factor is less obvious, why it's h cubed and not h squared or h to the fifth. This is tight. There's no other argument can be better than this. But it was actually an open question until this paper that satisfied this absolutely h cubed. Yeah.
So just for like to understand it, could you talk a little about what it means to say that there exist in algorithms that have like policies, or like optimization algorithms that would find a policy, or?
Yeah, it means that there exists an algorithm, meaning like it is this algorithm.
Oh,
that
or
they
algorithm in
propose.
particular.
Yeah, they propose an algorithm
I see.
that achieves this result.
I thought they proved something that's like this kind of algorithm
No,
exists. Okay.
There are results like that, but
Okay.
this is a real algorithm that you can run.
Okay.
It's the only reinforcement learning algorithm I've ever implemented.
So like what if states and actions are infinite?
Excellent question.
That's not a good equation.
Absolutely not. It's a terrible equation. So like, I said Atari. So what's the state space of Atari? It's freaking massive, right? It's all the pixels on the screen, all the possible states that they could be in, and the actions are all, the actions is pretty small. You can't do that many things with the joystick and things. But the state space is enormous, and this bound explodes. It's terrible bound. And so what people try to do is they try to approximate the state space by saying, well, I want to somehow group states together. So states that are similar get sort of like, kind of like clustered together in a way. And then I can sort of treat similar states as the same and then run an algorithm like this. But it's still going to take a huge, long amount of time because still that's going to be a large number of states. So you should never think of the number of states as being, infinite, but it could be, you should really more think about like the covering number of the states. How many sort of discrete states do I need to well approximate the continuous space? And it could be tons and tons and tons. And that's why Atari, the number of episodes that you need to run Atari for is in the like billions to learn anything, because these algorithms really are terrible. But this algorithm is actually very good. So for the states and actions, so like if you fix the number of states and actions, this is a very, very good algorithm for this problem. When there exists problems where you can get a much better bound than this, or when you can learn much faster, you're taking advantage of some structure about the problem. And you're taking advantage of, this isn't just some arbitrary sort of MPP or process like this, where you have like arbitrary states and actions that are unrelated to each other. In Atari, like there is, when humans go and play the game, we're bringing all sorts of biases with us. Like, oh, when I press right, it goes right. When I press left, it goes left. I can safely assume that on all future states, whatever the screen is, when I press right, it's going to go right. That's an assumption. Like, that's not necessarily how like the world would work. It's just like these games that we make for ourselves always follow our intuition. But if an alien came down and was unfamiliar with gravity and unfamiliar with normal physics, there's nothing that would say that that's how the world would work. You'd have no predictive model about how these video games would act. We're bringing a lot to the table before we even play a single second. And that's why we can do it, but an automated algorithm, somehow you would encode these sort of biases and bias herself towards good answers or good policies. Yeah.
Would one way of thinking about that be like if showing examples to it in a way does that? Like if you, like some algorithms allow having just sort of like human examples or just like teacher inputs, would that kind of be that in a sense?
Yeah, I mean, but even if I gave you like the optimal teacher to like tell you this stuff, like you would still not know. So basically what you could learn is that, oh, in all the states the teacher showed me and what actions it did and what happened, I know what to do, I know how the world acts. But what about all the other states that the teacher didn't bring me to?
That's true.
You have to have some way of connecting these.
Is there
And this
something-
is called like general function approximation. And this is where a lot of the neural networks come in.
Yeah.
But the problem is, in those settings, so when we do have algorithms that can solve Atari, the algorithms that run, we have no guarantee like this. We have absolutely no guarantee on the algorithms that are implemented in practice. All AlphaGo and that sort of stuff, it's just heuristic.
Yeah.
Some person can for the bound, it's an extremely inefficient algorithm. And if you would apply, so this is, yeah, okay, here's to put it in perspective. All the algorithms that we currently use for Atari and to play real world games, if you applied those games to like a simple game like this, it would get linear effect. It would be terrible. It would be a horrible algorithm, and you can easily trick these algorithms into failing catastrophically. And so that's why we have RL theory to build algorithms, and so we kind of come from the bottom up, where we try to understand really simple situations, and then make more and more assumptions to get more and more complicated, so that we can play more advanced settings. And we are getting closer.
I know this
We're
doesn't
still
add-
like 20 years behind.
I know this doesn't add anything, but I really like that way of thinking.
Me too. I'm curious.
Okay, so Andre and I were talking, maybe arguing, about like, so there's like this challenge from Francois Chalet about like abstract reasoning, right? Which is basically he gives you a couple examples of some like, it's kind of hard to describe, but maybe you have like,
I can pull up examples.
yeah, pull something up while I stumble over words. So maybe you have like a picture and it has some like pixelated image, and then it gets flipped in the next image, and then you have like 3 of those, and if they all get flipped, then as a human you can be like, okay, then if you give me something, I'll just flip it. But then the rules change every single challenge. So you get 3 examples and you get 1 test, and then you try to do that, and then you'll have another thing, and it's a completely different, the rules are completely different. So it's no longer just flipping it, it's like, I don't know, maybe you have to like rotate it, or I don't know.
Sure.
So
They're
then
very good at these tasks.
the challenge is like, well, Andre is saying like, you can't just interpolate to solve these challenges because the rules are different, so you don't have any points, like, it doesn't exist in between the points, the answer to the next problem. But my question is like, I don't know that like anything besides interpolation exists. It's just that humans have a lot more experience. So to us, it's just like,
Oh, like you're talking about intuition?
yeah, it's like, we don't really learn new things. We just sort of reframe them as old things, it seems like,
For
maybe, I don't know.
context, an example task looks like this, where you're given like just a couple examples.
Mhm.
So there's like a couple hundred different tasks, and you're given like literally just these 3 training examples, and this is the 1 test example. And every task has its own like variant of that. So like here's a totally
Yeah,
different
I
rules
get
for
it, yeah.
everything. And yeah.
Is there a question?
So the question is like,
Sorry.
can reinforcement learning kind of like
No.
bring anything to the table in terms of extrapolation? And in my, like, in your opinion, does what is extrapolation? How
So this is not a question of reinforcement learning.
okay.
Reinforcement learning is all about, you have state of the world. And if there's a current state of the world, I take some action that changes the state of the world, and I get some reward. And then I take another action that changes the state of the world. It's a very interactive process. This is more like supervised learning, where you have examples. Maybe it's very like one-shot learning or very, very small examples, but it's wrong to call this, I would say, anything but supervised learning. Well, okay, so maybe it's not supervised learning because supervised learning has IID assumptions to it. We assume the tasks are drawn from some distribution, and then I am trying to interpolate or I'm trying to generalize to data drawn from the same distribution. These kind of tasks, it's hard to argue that's what these are because someone is just coming up with these things. And so then you'd be like, well, maybe the person is generating these things by idea as IID. It gets weird. But I would say your argument, when it was your argument of you can't interpolate, I would actually push back on that. A lot of these tasks actually are interpolation tasks, in the sense that, like, in what space are you interpolating? Obviously, the pictures are changing, but like the task itself could be interpolating. If you consider, right, like if I throw this against the wall, I've never seen, that's never happened in the world before in this room. But I do know how physics works, and if I were to put this in some basis, then I would just fit lines to all of the atoms in the universe of things moving around, and then I fit that line, and then I say, oh, I can predict it perfectly, what's going to be there. And maybe on that particular line, I've never seen that particular line with that particular curve, but I've seen many curves like it. And so I'm interpolating in the sense that I've had lots of experience in understanding how the transformations work, or what could happen. So if I see an example of one, I can relate that to sort of a nearest neighbor in some space of like, well, that's kind of like this transformation that I've seen before. And even though the image looks very different, you're not interpolating between an image, you are interpolating semantically, where you are, yeah, you have seen stuff like it in the past, and therefore you know how to complete it, is what I would say.
Sorry to interrupt. What's the name of the paper that you're referencing?
Minimax balance reinforcement learning.
Okay.
It's something like that. If you type in those words, it'll probably be the first.
Minimax balance or balance?
What was that?
Minimax regard balance for reinforced learning?
Yeah.
Okay, thank you.
But yeah, I mean, these are questions of like AI, and it's hard. I mean, like, I think what's really nice is that a lot of people are thinking more deeply about this than they have because they're trying to come up with benchmarks for a lot of these language models. Because a lot of people are claiming that there is some like intelligence in these very large language models, and so people are getting very clever and thinking like, no, is it really just getting lucky? Like, it's just completing sentences and doing things that looks super cool. It's amazingly cool, but like there's not actual understanding there. It's just sort of mimicking people.
So this is kind of going back to an earlier point. Sorry, I know we're interrupting like a lot, but honestly, it's kind of the point of this.
It's your time.
So I was thinking about how you described it as not really reinforcement learning a task to do that one task where you tackle problems like one at a time. Would you say it makes sense to call it reinforcement learning if you incorporate like the state of like the knowledge of whatever agent as just like an aspect of the world or something, as something that.
So there's lots of ways of modeling these things. I really don't like doing that. So I tend to reject papers who do this because it's extremely misleading to do this. Like, you are you're building your self or like your learning algorithm into a reinforcement. Like, you're forcing it. You're forcing the reinforcement on the algorithm when there is no state. Like, there is just an understanding of the algorithm, or there is an algorithm and it takes an action or interacts with the world and it gets some reward, either getting it right or wrong. And that doesn't change what happens. That doesn't change the state of the world. It doesn't change which one is going to get next.
That's true.
It's the state of the world has stayed the same, or it gets IID draws from the state of the world every single time. It doesn't matter how you do it in the last one or the next one, you're getting this one.
Yeah, it's true, this isn't.
Now, like in a GRE or like an SAT, these adaptive tests, that is a Markov decision process, or that is that's a reinforcement learning problem. Because there, based on how you're doing, whether you've gotten things right or wrong, the next question you get asked is based on everything in the past. And so how you're answering is actually changing the state of the world.
Wait, it is? Like when you have like a paper test and you're like,
Not a paper test, I'm saying like a GRE or SAT, those are adaptive tests, that's why you take them on a computer.
I took them on paper.
But we're thinking of different tests, because,
It's like,
well, are you talking
like a
about
couple
like,
years
what's
ago or
the high
something.
schooler state? Or,
I thought so. Maybe it's just
SAT
GRE.
at least, maybe the GRE is like that.
Oh,
I
okay.
don't know.
I thought they were all adaptive. I don't know.
No.
I mean, it doesn't matter anymore. UW is not requiring them anymore. So,
well, let's suppose there is some adaptive test,
yeah,
that's what satisfies this.
Sure.
all my examples are dying. Yeah, so like this is what we study. We like, and like we try to prove regret bounds, or like how long does it take to find a policy, so that we can be very sort of clear about quantifying how difficult a particular problem is, because that's understanding. To me, understanding is predictability. Can I actually, if you tell me what a problem is, I can tell you, how hard it is going to be to learn.
Sort of an element of simulatability, like, can you understand algorithm in a way that you can, without actually running it?
Yeah.
Talk about how it's gonna be.
Exactly. A theorem is basically a simple way of doing an infinite number of simulations. So if you prove that this algorithm achieves this regret bound, what I could do is try all possible environments with S states and A actions and horizon H, all possible ones. I just enumerated them and then ran them all and then checked. Yep, they're all less than because of this bound. A theorem is just a way of simulating that without doing any computation.
Is there any understanding whatsoever for why all of these big algorithms or big systems like AlphaGo or whatever, even though they have all these terrible bounds, why?
But they don't have bounds. They don't
Oh
have-
yeah, I mean their bounds are basically infinity.
Yes.
Is there any connection whatsoever as to why they work anyway, or are they just not remotely studied from this perspective?
No, we're trying to. It's hard. I mean, this is as simple as you can get, and we just proved it 5 years ago. It's and this isn't me. This is authors from.
DeepMind, right?
What was that?
It's DeepMind according to this paper.
Yeah, Azar and Ian Osmond are DeepMind now.
Oh, the paper says it's from DeepMind, so.
Oh, okay. I think Ian was speaking about this stuff when he was at Stanford, but yeah, he went there after his PhD. But I work in a lot of problems like this. So this is a regret bound. What my work is mostly if you don't get charged for learning, so all you care about is learning the a good policy as fast as possible, then how do you come up with algorithms that learn the policy as fast as possible? So these are slightly different. So this is a regret algorithm, so it means that if I did really bad on some episode, that's gonna stay with me forever. But that's not how we actually use RL a lot of the time. It's a very nice, theoretically beautiful framework to study in. But in reality, when you think about Atari, what they do is they actually do, you learn an RL algorithm for Atari, and then once you have that algorithm, then you have it play. It's not this ongoing thing. You're not accumulating reward over time. It's just you're trying to learn a policy that does a good thing. Just like in a doctor's or in a healthcare situation, you're not going to just deploy this thing out in the wild. You're going to learn a good policy, have it vetted, and then go deploy it in the world. So many things in practice are actually not deployed online. It's deployed in this offline manner. So you first do exploration in sort of a test environment, you're very happy with the result, and then you deploy it.
Yeah.
So I do consulting for Amazon, and we do this constantly in robots. We're not doing any learning in real time. We always collect lots of data and then learn a good policy, make sure it passes a bunch of reality checks, and then we deploy. Because a mistake is extremely costly.
Like this is especially true in like a lot of the more finicky optimization systems. But like if you just keep training something infinitely, it could just kind of break.
Yeah.
The gradients explode, and then you're screwed if it doesn't have balance learning online.
Yeah, that can happen. And
Yeah.
also you can get horrible feedback loops, and it could be doing really well, and then some person comes in and starts poisoning with data, or like something, or not even corruption, or not even like adversarial, but like if you have some robot and like the lighting condition changes or something, or like a sensor breaks, and it starts learning really terrible things that it never forgets.
Yeah.
And so this is all things you kind of need to be worried about in real life. But yeah, maybe I'll give, last like 20 minutes or so. I want to show you like a really simplified system, even more simple than this, where I can show you where this comes from, and like how do we get to a bound like this. And so we're going to start with multivariate bandits. So this is reinforcement learning, but we're going to be interested in multivariate bandits. It's a different color. So multi-armed bandits. So here the game is, we just have no states, we just have A actions, and no horizon. It's a very simple game. It's basically you start at S1 and you stay in S1 forever, and there's only one time step. It's the simplest possible game, but you do have A actions. And so now it's going to be for t equals 1, 2, ... Player chooses AT in A, and nature reveals, let's say RT drawn from, say, like data of AT1. Okay, and this is a normal distribution. So there's some vector theta, and when you take action AT, you receive some random reward with mean theta of AT. Okay? And now the regret, let A star be equal to argmax of A and A of theta A, so it's just the one with the highest mean. And then your regret, after t time steps, is defined as being the expectation of theta A star, what the best got, minus theta of AT. Okay, so this is the reward that the single best action in hindsight got. And this is the amount of reward that you got where you played AT at each time. And then you received a total, and this results in some regret. Okay. Is the setup clear, Deborah?
Yeah, it seems overwhelmingly simple. Like, is the points to prove that kind of low upper bound on this simplified setup?
Yes.
Okay.
So this problem was proposed in the 50s, and is a big part of why how you're shown ads. And if you ever go, how you're shown Netflix, recommendations, Spotify, Amazon, like if you like this, you probably like that. All that sort of adaptive sort of learning and applying to you is all multivariate bandits. But usually they try to add in feature vectors and things like this, which we're not going to talk about today. Totally different setting. But we're going to do this. Okay. Algorithm is going to be UCB, upper confidence bound. T algorithm. This was invented by Bohr et al. In like 2001, maybe? Somewhere around there. Give or take 2 years. Okay, at each time, it's going to let theta hat AS be empirical mean. Of the poles from arm A at time t. And let TA be just the sum. Like AT is equal to A. Okay, so it's just the total number of times I've pulled arm A. Let's say it's like a T. So this is a function of T. And now, what we're going to play, what AT is equal to, is just equal to argmax A and A of theta hat A T A of T plus some constant times 1 over TA of T. Okay? They're constant, it can go to 2, but I'm not going to talk about it today. So, okay, so at each time T, TA of T is the number of times that it played arm A up to time little t. And so, and theta hat is the empirical mean of TA of T poles. So at some time little t, I pulled some number of arms. Sorry, I'm calling each action an arm. And so basically, the algorithm we should play is arm AT, which is the one that maximizes the empirical mean. So this is, if I just had this, the empirical mean, that would be the greedy strategy. Just given all the observations at the current time, I just play the one that looks the best so far. That would be the greedy strategy. But then I add in this little bit of bonus. It's 1 over square root of TA of T. Okay? And this kind of algorithm, the idea is optimism in the face of uncertainty. And the idea is, the picture you should have in your head is that the way I choose C is such that this value is an upper bound on the true value of theta of A. Okay? So, fact. Just take it as a fact that theta hat A S minus theta of A is less than or equal to the same constant divided by 1 over S. Okay. So if I take the first S observations from the 8th arm and compute the empirical mean, so if I take the empirical mean of any of S observations from the 8th arm, then the deviation of that mean away from its true mean is going down like 1 over S, the square root of 1 over S. Okay. And now, how long do we have, by the way?
We stay here till we get tired of talking, but you are
Okay.
free to go whenever you need to go.
Okay, I'll give it another 10 minutes. I'm almost done. Okay, so this is just a fact. And this is going to be extremely important to our analysis. Because what it means is that this guy is basically, because I'm having its empirical mean plus C times 1 over square root T, because of this inequality, that automatically means that this quantity for all A simultaneously this guy is always at least greater than or equal to the true theta of A. Okay? So this is always greater than theta of A, but what happens? We know by the law of large numbers that as t of t goes to infinity, so we pull this arm an infinite number of times, the empirical mean will converge to theta of A, right? And because of that, we also know that if, as t goes out to infinity, this guy is going to go to 0, right? And so, but because we have, let's say let's say our means look like this. Okay, these are our arms. Then if these were, say, like the true means or the empirical means, suppose that like TAT is so large that like this, they're all sort of converged. Then the confidence bounds, if at each time I start with some confidence intervals, or I start, because that's what this is. We're basically saying that the empirical mean minus this true mean is bounded by this confidence interval. So think of this as a confidence interval. And so what it's doing, if I were to plot this value for each one of my arms, and I'd have something that looks like this, and they'd all be basically and then if I played this algorithm, if I always choose the arm that had the biggest upper confidence bound, the one that had the biggest theta hat plus 1 over root t, and that's what this value is here, each one of these little caps, then what's going to happen is when I pull that one, when I take that sample, this is going to decrease because I've added 1 to the number of times. And then also this is about not going to change that much, because it's sort of converging to its true value. And so like intuitively, if I always pull the maximum one, it's going to shrink that one. And so over time, if I keep doing this, it's basically a strategy that's going to minimize the maximum upper confidence bound. And this is a really cool strategy, because eventually what's going to happen is that these are going to shrink, these are going to shrink, these are going to shrink, until this guy can't be shrunk anymore, but these guys will be just at that same level. But at a certain point, this one can't go any lower, right? Because we have this property. So for the best arm, his value cannot go below his true mean. It's always going to poke a little bit above. But all these guys, if it poked a little bit above that one, then we're going to play that one, it's going to get knocked down. And so actually, the number of times that you can even hold this arm is the number of times this will be picked is bounded. Because if I kept, here's a proof by contradiction. Suppose you could pull this arm an infinite number of times. Well then, the 1 over t of t would go to 0, and this would converge to a true mean, which would mean that the blue thing would go all the way down here. But if at some point it had to cross sort of like the halfway point, but if it was at the halfway point, it would have a lower UCV than the best arm. Therefore, it wouldn't have been played. So it's a proof that like every suboptimal arm will be played a finite number of times. Okay. But now, and the key of this analysis is that theta hat 1 t1 of t, or a star, plus c times 1 over t1 of t, this is always at least theta a star. And the reason why this is important is because for our regret decomposition. Okay. So consider at time t how much regret we're occurring at time t. So at this time t, so the beautiful fact, on fact one, given fact one, and the algorithm, we have that theta hat AT TAT of t plus C1 TAT of t was greater or equal. It's the only thing we know. A star TA star of t. And we don't know what this arm is, but we know that because the algorithm chose one of the highest one, this AT, we know that it was at least as big as the best arm, which was A star. And that is at least as big as its true mean. Okay. I haven't really said anything. I'm just sort of pointing out this very cool fact. So fact 2. Okay. So now the regret at time t to big T, as we said, was equal to theta of A star minus theta of AT. But this is equal big T of theta of A star minus theta hat of A star TA star of T plus theta hat AT of TAT of T minus theta AT plus theta hat A star TA star of T minus theta hat of AT TA T of T. Okay, so all I did was add 0. I just added and subtracted theta hat A star and theta hat AT. That's all I did.
Could you take 5 seconds to go over what each of the thetas and theta hats represent in this context?
Yes.
There's a little too many thetas for me.
So the theta is like the true means.
Yes.
So these are the true means. So theta A is the mean of the 8th arm.
Yes.
And then theta hat A, TA of T,
As we learned.
is the empirical mean of the first TA of T poles of the 8th arm. So it's just if we've pulled it TA of T times, and it's our empirical mean. Okay? Now, what's great about this is that, maybe I did this, never mind. This is a different proof. Sorry, there's like many ways to prove this, and that's not the one I wanted to do. I'm going to use this fact 2, and have this theta A star, and then upper bound this guy here. Because this happens at every time t. So then this guy is less than or equal to theta hat AT TAT of t plus C 1 over T AT of t minus theta of AT. Okay? This is great. This is really fantastic. You can tell me why?
Doesn't this effectively represent like how many times the form of the regret in terms of like how many times the big pull sort of?
Yes. Yeah, but the beautiful part is that we have theta of AT here and theta hat of AT here. And we have fact 1 that relates empirical means to their true means. And so I can actually, because it's the difference of these two, I can upper bound this thing by t equals 1 to t of 2 times this guy. Now we're cooking, right? This is great news because this is decreasing. Right now it's becoming very clear that the regret cannot get arbitrarily big because every time I play t of t, it gets smaller, right? So yeah, and so we can now do something cool, which is I'm going to then say this is now I'm just going to sum over all my arms. Big T of 2c of indicator that AT is equal to A, 1 over TA of T. So all I'm doing here is I don't like this AT dependence. It's kind of gross. So what I want to do is I just want to sum over all my arms, just have an indicator of whenever AT is equal to A. So I haven't done anything, but it really cleans up the math. Because now, what's going to happen? Well, let's think about what happens here. If AT was equal to A, this sum is going to increment by, this TA of T is going to increment by 1 for the next time until it's pulled again. And then it'll increment it again. Right? So it stays constant until it's incremented at the next time AT is equal to A. And so what this actually is it doesn't change, and it also doesn't contribute to the sum, unless this indicator is on. And so this sum is actually equality, sum A equals 1 to big A, of the sum from S equals 1 to TA of big T, the last time it's pulled, of 2C1 square root of S. This is a little tricky. But like, you have to think about every time this is actually incremented. Think about only the times T that this actually is non-zero. Right? The only time this is non-zero is when AT is equal to A. And at that time, when AT is equal to A, TA of T is then incremented by at exactly 1. And so this is exactly this, where this factor is never going to get bigger than TA of big T, the final time T, because that's the end of the game. That's the final time at which it's going to be. But every time in this sum, it's incrementing by 1. And so this is actually equality, where I sum from S equals 1 to TA of big T of 2C of 1 over root S. Is like the key step. Because now, what is from S equals 1 to K of 1 over root S? What's the integral of 1 over root X?
Natural log.
No, that's 1 over X.
1 over root X. Oh.
Integral from X equals 1 to Y of 1 over root X.
Square root 1 square root X.
It's square root of Y, yeah.
Yeah.
And so this guy is then equal to the sum over A equals 1 to big A of 2C times square root of TA of big T. Okay, starting to look pretty good. But I don't know what TA of T is. This is sort of awkward, sort of a function of my algorithm, not like the fundamental parameters. And so then we apply Cauchy-Schwarz, which everyone in my machine learning course should know.
I remember the name.
That's good enough. And what it'll be is, I'll prove this in a second, I'll write down what Cauchy-Schwarz is. It's going to be A times 1 big A of TA of T. And this is exactly just summing up all the poles from all the arms up to time big T, which is equal to T. then this whole thing is just equal to 2c square root of at. Okay? So what's Cauchy-Schwarz? There's two key technical pieces in this proof. It's this piece, it's going from here to here, and it's Cauchy-Schwarz. So, Cauchy-Schwarz for x and y in Rn, we have that x, y, let's show you the x, y2. Okay, that's a Cauchy-Schwarz. It's how do I get this from that? The Cauchy-Schwarz. Any guesses? Just stare at it for a while.
Which one? From which one?
How do I get from here to here? This is inequality. How do I make that true? Using Cauchy-Schwarz. Well, maybe I'll write this in a more suggestive way. How about now?
So you can like move the sum from the actions in somewhere, and then
So what is my x and what is my y?
TA is x, and y is something to do with the actions.
I mean, you could say it's like a vector containing ones.
Yeah.
It's kind of, yeah, I was thinking about it with that being x and the other thing being y just because ordering. But then.
No, that's exactly right. So this would
That
be.
expression is basically a dot product of that vector containing ones times the square root of TAT thing. The 2c just kind of gets factored out.
Yeah, the 2c can come out front, that doesn't matter. But if we call this xa and ya equal to 1, then the sum squares of the ya squares, this is going to be equal to n, which is just equal to a. So we get our a there. And then the sum squares of the root ta of t is just the sum over all the ta of t's. And so we just get this, and then this final value.
Yeah, that really simplifies it.
And so that's multi-term bandits. So now, how this relates to this is what we do is, what do we, to think back on what we just did here, we made an optimistic estimate of the true mean. So we overestimated the true mean by something empirical plus a confidence bound. Okay, that's what this algorithm critically did. And then I took the action that I was most optimistic about, right? And it's called optimism because I know the true mean of this arm is less than or equal to this, right? And so, but that's all I know. I only know it's less than or equal to this. So what I'm gonna do is be extremely optimistic and just play the arm that it could possibly be the best, right? And then I'm just gonna repeat this strategy. So what do you think I'm gonna do in the MVP case? What I can do is for each policy pi, so for every map from states to actions, I'm going to build a confidence bound on the value function, on the amount of reward that the policy pi could return. And then if I can prove some upper confidence bound on it, meaning that if I can have sort of the empirical quantity plus some bonus, like this is 1 over TA of t, then what I can do is I have optimism, Meaning that the best policy, the upper confidence bound is always at least the value of the best policy. And then I'm gonna keep playing those, so at each episode K, I'm gonna play the policy with the highest upper confidence bound. I'm gonna keep playing that, and eventually, this is the exact same picture, but instead of arms now, it's gonna be policies. And then eventually, the proof goes down very similarly, and you get, I mean, the key steps of the proof are identical. It's just like, the proof of that is like 10 pages versus this is like half a page. But like, it's just technical. Like, it's not, these are the big steps behind getting the algorithm to work. I'm doing something about it.
So in the end, the states aren't actually that important. It's only like relevant in terms of the number of possible policies, because like.
Yes.
Yeah, because it's
That's
just,
accurate.
it's the same as just like what the arms are actually. That's more just
So
how many there are.
okay, let me caution you there though. There are an exponential number of policies.
Yeah.
So that's not quite true, right? Because let's count the number of policies that there are.
Oh, I don't mean it as linear, like sort of.
Yeah. But yeah, like intuitively, yes.
Yeah, I just mean like you don't have to think about like what the states themselves actually are. Like you just think about abstract as policies depending on
Yes,
states.
exactly.
Sure.
You're making inferences over policies, not over what states and actions they're actually
Yeah.
using.
That seems like a really like clever leap, even though it's not that complicated to like.
Yeah, it's not that complicated. Yeah, and so, any questions on what we talked about so far? So like, if you like this stuff, take my interactive learning course. Unfortunately, it's not gonna be offered next year.
Do you plan to have it offered the year after that?
Yeah, it's moving to once every 2 years,
Okay.
so I can introduce a new course next year.
What's the course next year?
That's gonna be the advanced machine learning course that Luke is gonna teach. He's gonna teach it, I'm gonna be making course materials for it, and probably lecturing some.
Oh, that's pretty. Might as well take that.
And if you're interested, there's great books, amazing books on this now. We're very lucky. You could also, I have like 6 hours of lectures on it on YouTube. You also go look at that. But yeah, this is one-term bandits and reinforced learning theory. There's a lot of questions that we get asked from here, but a lot of them have to do with function approximation and what assumptions can we make on our states and actions so that we can remove this explicit dependence on the number of states and actions.
Can I ask like a question that might be a bit silly, because maybe it's just my intuition doesn't line up with the math properly at the moment. Hopefully. Anyway, so the point is that the upper bound on the estimated mean never like dips below the true actual mean.
Yes. Well, the upper confidence bound doesn't, yes.
Yeah. So even if you like end up just like, because it is a normal distribution in this case anyway, like what if you just end up getting for 500 times in a row, like 200 standard deviations below the mean, and it just ends up to saying that it's really, really low.
Okay,
even when
this is a
it's-
really good question, or observation. So I'm claiming that this is a fact. What exactly do I mean by that? What's hidden behind this is what I actually mean is with probability 1 minus delta, for some very small delta, take delta to be 1 to the minus 6, this holds.
Yes.
For C equal to like 4.
Yeah,
Okay.
that's kind of what I was thinking about with that. Like
So all of this analysis only holds with high probability. The true statement is saying, with probability at least 1 minus delta, the regression is bounded by square root of 8.
Yeah. And we can talk about those probabilities very simply by the fact that we just assume it's a normal in this case.
Yeah, it turns out that that's not that significant. You can do all sorts of, there exist very fancy estimators for like heavy tail distributions and things like this. And it is actually, in general, if you have 2 moments, like if the variance is not infinity, so like a Cauchy distribution has infinite variance, you can do that. But like everything nicer than that, you can prove this kind of inequality for some constant C.
Okay.
With high probability.
question was something like, what would you like choose to research or explore in the field of like reinforcement learning if you did not have any constraints?
What would I?
Mm-hmm.
I don't have any constraints.
You don't have any constraints?
I would do my current research program.
Okay, what is that? Explain that.
So a lot of what I do now is I look at situations like this, and I add function approximation to it. So it's basically like saying, you guys familiar with Q values, Q functions?
Yeah.
Q learning?
Mhm.
Yeah. So like function approximation would say, well, I'm going to assume that Q of SA is equal to F of SA for some function F in some class, like a neural network or something like this. And that class has bounded complexity in some sense. And if you want to know what I mean by bounded complexity, you should go take the advanced machine learning course. I mean things like Rademacher complexity or VC dimension, covering numbers, metric entropy. And then try to prove regret bounds or pack learning, the number of episodes of where I can output an epsilon good policy, and how to do that. So my specific research is more on the pack learning side. PAC stands for probably approximately correct, because you output a policy that is with high probability approximately correct, and the game gets much more difficult than this. This is a worst case bound. We call these bounds minimax bounds. We call them minimax because they just depend on very coarse quantities of the problem, like the number of states, actions, the horizon, and the number of episodes. Okay, very coarse. I work on instance-dependent bounds, and so this regret would depend on a lot more than just the number of states and actions. It would depend on what these probabilities are and what these rewards are. How difficult is it to get to another state? If it's very difficult to get to a state, the optimal policy can't go to that state either, so I can ignore it. But if this, if it's very easy to get to a state, then I should obviously go and explore there. And so it's all these intermediate states that are kind of difficult to get to, but not impossible. How much effort do I put into those in order to learn a policy as fast as possible? And for that, we are, so these are basically the benefit of instance-dependent algorithms over minimax is that they basically adapt to the true difficulty of the problem. Okay, so minimax is a worst case bound. This holds for any MDP, for any P and any R, such that it has a number of states and actions bounded by this. But my algorithms that I developed in my lab, they are instance dependent, and so I'll put some other regret bound that will depend on P and R, but the point is that this algorithm is actually better than this algorithm. We can prove that our algorithm will actually adapt to the true difficulty of the problem, and the bound will be much smaller, meaning the algorithm will perform much, much better when the problem is easy, when the environment's easy, and will never be worse than this. This is a worst case bound, but our algorithm will actually take advantage of easy situations. And the motivation there being that nature is not adversarial. We're not picking, nature is not going out and trying to make us the worst world possible. It just is what it is. Sometimes it's really easy, sometimes it's really hard, but we're an algorithm that adapts to that difficulty. And the hope is that by using these, by going after these instance-dependent results, is that when we do go to deep reinforcement learning, these more interesting sort of settings, if they are easy, so the fact that a target is learnable is an existence proof. And so when we build up to those, we will be able to find an algorithm that efficiently can learn and provably has guarantees. That's what I work on.
Gotcha. Kind of.
So are you building it upon Q learning, or are you building it upon this, or kind of just whatever?
I don't constrain myself to any algorithm.
Yeah. Okay.
Wait, is this also called SARSA?
No.
Okay.
SARSA is a specific algorithm for doing Q learning. This algorithm is done, it's more doing value iteration. it does value iteration on the UCBs, essentially. And so in typical value iteration, you just sort of pass back the values from the Q function to do the argmax of QSA. Instead, this algorithm is doing argmax of QSA plus some bonus term, and then passing that all the way back. And then so it's basically planning in a very optimistic way. So SARSA is an algorithm that we know some things about, but we also know that SARSA does fail. We know that it can get stuck, like on a problem like this. It works, it's a very good heuristic, but it can get stuck as well.
I was also wondering, like, when I look at Q learning on the internet, it often relates to the brain, and I was wondering if you know anything about that.
I'm not gonna comment.
Okay.
So you need to know the transition, like the probabilities of transitions for this.
No, you estimate them.
Okay.
So this algorithm, great question. So we built upper compass bound just based on the rewards that came back, right? But now we have transitions that we don't know. And so what we're gonna do is we're gonna build empirical distributions of our transitions by just counting. If every time I'm in state S and I play action A, how many times do I transition to state S prime? And just get an empirical count of that. And so then my MDP, I have some estimates that in terms of like R hat and P hat, and I can build an upper confidence bound on the entire reward function based on those estimates of R hat and P hat. So that's what makes it more complicated. That's what adds the 9 pages of analysis, is dealing with that P hat.
Gotcha. Any questions that aren't from Yegor and I?
RL is extremely exciting. There are so many problems that are open. Like I mentioned this out for it all in 2001. Like, so Bandits, it's like got extremely, the area, like so, I'd say like in the late 2000s and mid 2010s, multi-array Bandits got incredibly popular because it came up sort of like with the internet of like everyone wanted to optimize everything and doing, you know, adaptive A/B testing and trying to make as much money as possible on ads. And so like multi-array Bandits became extremely popular, and now the only problems left in multi-array Bandits are insanely hard. They're just really, really hard, and it's hard to make any progress at all. They're like the kind of students that I feel bad giving to a graduate student because like they could easily spin their wheels for 3 years and get like nowhere. Reinforcement learning, way more complicated. It takes a lot longer to like get that base knowledge, to like understand where the frontier of knowledge is. It's just a lot more notation and just stuff that you need to learn. But once you get there, making a contribution is not that hard because so little is known about it. It's just easier to make a contribution because it doesn't have this enormous following or this enormous amount of work in it yet. So it's a very good time for reinforcement. It's very fun. Also, another area that we haven't talked about at all, this is all stochastic. Another very cool area right now is multi-agent reinforcement learning, where you have actual gameplay between 2 players. There's nothing stochastic about the game of Go, for instance, or 2 people playing StarCraft, because they're interacting with each other. There's nothing stochastic about that. And so that's a even less explored situation that we know almost nothing about.
This is kind of a completely unrelated question, but do you have any good book recommendations or like any recommendations of papers to read regarding this, or I guess machine learning as a whole, though not including the obvious like textbook for machine learning?
So Lattimore and Bespari. This is called the Bandit Book. They literally wrote the book. reinforcement learning, theory, Agarwal, et al. This is 2020. And this is 2020, I think, as well. And it's called, I think, the theory of RL, reinforcement learning. You can, you asked me what book is that for?
Okay, wait. So, this one is,
Yes, that one.
which one? It's not the Bandit one, it's the theory of RL.
Yeah, the theory of RL.
Okay.
I go on, it's called, yeah, it's called the theory of RL. Alec Agwal and Sean Cockaday and Wei Sun. This one. And then this is Lattimore Chapsari. The Bandit Book. You can email me if you can't find it. But they're big.
Is this the right? It's called Bandit algorithms?
Yep.
Okay.
They're basically like, by far the best and most popular books on this topic, so shouldn't be too bad. And this one is very self-contained. You can read it front to back, and it will give you all the probability background you need, which is, for some stuff, significant. Because basically, in machine learning and even stat learning theory, so if you take the advanced ML course, we all are very interested in IID sort of things, trying to prove stuff like this when data is drawn IID. When you start doing adaptive stuff, your data is collected adaptively, it's not IID anymore for very subtle reasons, and these kind of bounds don't apply anymore, and so you need new tools in probability theory, and it gets tricky. But book does a good job. It's how it's so easy these days. Oh, so many good books.
Too many books.
Too many to take time to read.
Yeah, it's a good problem to have.
Yeah.
It's funny, like, this always happens, but like, my colleagues and I always sort of like joke, they're like, yeah, grad students have it so easy. Like, they don't have to go read like the obscure, like, 1,000 papers. Someone just like put them all in a book, and it's like summarized in a nice cohesive story.
I read obscure papers all the time. I don't ever read books, I don't know. Well, that's not true, I don't ever read machine learning books. Maybe I'm just,
I always would prefer a book over a paper, because books, someone sat down with the intention to teach and wrote this book in a very particular way. No one does that with a conference paper.
I don't know, some people do, like, do you know if Christopher Wallace's work? I feel like he does that. He's more like in AI, like interpretability and just explain, or just like, less interpretability, more like, I don't know what to call this field, but just like understanding the internals of like neural networks.
Okay.
Just like making visualizations of what's happening, but like, some people are really, really good at making their papers explain things well.
Yeah, well, there's explaining things well, and there's also, but there's like, I don't know, there's like, it's a different style of writing to write, to explain what your contribution is, which is what a conference paper is.
Oh, yeah.
Like, the vast majority of the paper should be your contribution, right? That should be at least 80% of the paper. But a book, it's like none of your work. Like, you're not, the objective is not to describe what your contribution of this work is and why it should be published. It's just self-evident that this stuff is important in a book, and there's no ego in it. There's no, it's really, and it's not pulling from some sources, not others. It's only using like the best proofs. Like a lot of, so that's another reason I have a book. The original proofs are horrible. Like the proof of this result, do not go read this paper. It's awful.
I changed my mind about reading it.
The original proof of this is just so bad. Actually, the best proof I know of this is in my notes. It's not in the Agarwal book. They take 20 pages to prove it for no reason. I have no idea what they were thinking. I have to, I think they're going to change it to mine. Because it's just like a really simpler proof of this result. Because just like multiple iterations. Like, the only reason why my proof is simpler is because I read Ian's proof, and then I read Alec's proof, and then I saw sort of like another sort of, Alec vastly improved upon Ian's proof, and then I saw something that Alec didn't see to make it even simpler. And so that's why a book is so great. Like, you don't need to, it's not just like the first one is proving it, which is gonna be terrible proof, and dirty. But like, you're writing a book, like you sat down, you really thought, what's the fastest and best way I can write this proof?
Yeah.
So like for books, isn't it? Like you don't, like, do you just sit down and read like a machine learning book? It's like, don't you feel like you need a reason to want to like read through these proofs?
Yeah.
Cause it's like, for me, it's like, okay, I'm doing something, I don't know what I'm doing, then I go Google it. It's not like, okay, here's
Yeah.
a book, I'm gonna sit down and read.
Yeah, I mean, you're working in the area, you're working in, the area you go and read that.
Yeah.
Like, I've not read every chapter of Gladmore and Chavez-Mari, for instance.
Okay,
I read most of it by this point, because I've taught it.
right.
But like, no, I typically don't just sit down, I never read a textbook cover to cover, I don't think I've ever done that.
Okay, so I'm not like crazy.
No, I don't read textbook cover to cover, but like, if a textbook has covered a topic, I'm definitely gonna try to read it there first.
Okay,
Yeah.
gotcha.
Makes a lot of sense. There's also like, in a paper, this is less applicable to theory and more applicable to like experimental and just like in practice things. Like, they're always gonna try to make their method look good. Half the time,
Oh,
they
yeah.
don't even bother doing a good implementation of baselines. And then it's basically just lies unless you can like sort through what the other baselines actually are.
Yes, this is a particular problem in reinforcement learning.
Yeah.
I don't really trust any empirical result I've ever seen, unless I know the person that did it. And even then, who knows if a student got in there and screwed up something. It's a major, major problem. All right, I gotta go.
Anyway,
Thank you so much.
Thank you so
Fun.
much.
I hope this was
Yeah.
at least a little bit interesting.
That was very interesting.
Thank you so much.
Thank you.
Thank you.
Have a good one.
Thank you.